And did anybody recognize this from the PDF at all?
I remember, I've seen this before. I don't know.
That's
I didn't look at the PDF very much.
It's exactly, when I put something up like that, I usually draw from it. And it wasn't in any way, shape, or form meant to be tough. We actually did a problem almost identical to that.
Yeah, similar to. They said there was circular.
We did one with a lifting force, remember? It was rectangular. We just
I do remember that, yeah.
Okay.
It's not
All right.
so-
Sorry. I thought it was
I thought it
giving
wasn't
you a gimme,
so
but
bad. That's so stupid.
it was meant to be easy. Trust me. I wasn't trying to cause you any grief.
I don't know where I put a pie in there. Just I don't know how you put. I thought it was a circle, even though it clearly wasn't.
I've heard people
unfortunate.
tell me it just felt like stuff like that. It felt like pie. That's.
I hate to see it.
Well, listen. We're going to move on. Last time I was going through the time-varying form of electromagnetic field equations. What I'm going to do is this. I'm going to follow Whitworth's his ideas in his book, and this is going to be in chapter 5. And remember, it's now time-varying effects. So things are changing with time, and it gets complex, but here's the real deal. So remember, I put down the entire Maxwell's equations that first I had curl of H was actually equal to J plus the partial of D with respect to T. Let me see if I can get a better marker. Does everybody remember that one?
Yeah.
And
Sure.
I can write it larger, but I'll tell you what, I will. So curl of H is equal, this is fundamental, J plus the partial of D with respect to T. And I put down curl of E is equal to minus dB dt. These are time domain equations, and I'm going to leave them as such. Then there's coupling effects. J is equal to sigma times E. Sigma is the conductivity. D is equal to epsilon E. Epsilon is the permittivity. And then B is equal to mu H. And H is the magnetic field in amps per meter. Now, these couple of them. Now, we can play with this. I showed you how I was going to the phasor domain. Before I go through the phasor domain equations, I'm going to try to follow up what he does in his book with the next step, getting the actual value of. He has a time-varying form of the charge density. And I want to go through these. These are very straightforward, but people tend to make mistakes because they don't understand one of the relationships. Usually it's a relationship between D and E. Okay, we're going to start with this one right here. By the way, does anybody remember what this law is referred to? What if it didn't have this on? What would you call that?
It's just
Ampere's law, right?
Ampere's law, yes.
It's Ampere's law, and it would be for a point, right? It's the differential form. This is still called Ampere's law. Do you remember what this one is called?
That's Faraday's law.
Michael Faraday's law of induction, exactly right. All right, now, if we start with this one, we're going to work with this one. And we take the divergence of the curl of H. That is by definition 0. Divergence of any mathematical function that's the curl of another function is 0 by definition. And that's equal to divergence of J plus the partial of D with respect to T. Now, at this point, I'm going to show you a couple things that happen here. And there's more than one way to cast what I'm about to show you. So because D is equal to epsilon, well, I'll do it this way. First, I'm going to go ahead and say, I got to write divergence plus d dt of the divergence of the particle. Y'all follow me on this? I simply took a divergence of everything. Divergence of curl is 0. Divergence of J plus divergence of D, right? And what is the divergence of D?
Oh.
Volume charge density. Do y'all remember that?
Mm-hmm.
So now I have this. I have divergence of J plus the partial with respect to T of rho V. This is one form that we'll use it. That, by the way, is called the continuity equation. Does anybody remember, they call it Kirchhoff's current law?
Yes.
All right, it said whatever goes into a junction flows out of the junction or stays there. This is the differential form of that. If you didn't have this, it would be whatever flows in, flows out. That's what divergence of J will tell you if you integrate it over a surface. This will say stays there. It would be the development of charge or the accumulation of charge at a point. So charge density actually. Now you can do this too. You can say that J is equal to sigma E. Can you all follow me on that, right? And you can further say that J is equal to sigma, but E is equal to D over epsilon. So you can say sigma times D over epsilon is J. Can everybody follow me on that? The only thing I've done is say J is sigma E, but E is D over epsilon, right? Be comfortable with what I'm saying. Y'all agree with this, class? So over here I can also write this as 0 is equal to divergence of, well, sigma and epsilon, assuming that they are not spatially variant, can come out in front, and I have divergence of D plus D rho V dt equals 0. Or I can say 0 is equal to, and then I can just say it's sigma over epsilon times rho v plus d rho v dt equals 0. Can you all follow me on that?
Yes.
Now this is a simple first order differential equation. If I look at this, let me write it over here. I have d rho v dt plus, and then I have rho v. It's usually written as rho v here over tau equals 0, and tau is equal to epsilon over sigma. And this is a form that's very common. Now, do you remember how you solve differential equations like that? I mean, this one's really simple. You can do it any which way you want. Anybody? I'm going to tell you, on a job interview, I can't say they would, they usually do something where they just make sure they're checking all the boxes. The kid isn't one of these guys that pass through a course or you just, multiple choice kind of deal. So they'll ask you things like this. How do you solve this kind of different cube? Now, there's a lot of ways. You could use what? Laplace transforms. You could do it. Well, this is one of the simplest ones. If you take a look at this, we could say what? Rho v over tau with a minus sign is d rho v dt. Do y'all agree with that? Mm-hmm. Now, there are no source terms because it's a homogeneous equation. And then we could say that, well, I could take d rho v over rho v is equal to minus 1 over tau dt. Can everybody follow me on that? Just divide by rho v, right? Multiply by dt. Everybody? Now, what happens here? If I integrate both sides, this is like integrating 1 over x dx, right? Correct, class? Mm-hmm. So that's natural log. So I'll come from here and I get natural log of rho v is equal to, and then the integral of that is just going to be minus t over tau right here. You can add a constant if you want right there, but it doesn't really matter. And then you can see that rho v of t by, since this is natural log, take e to this power, and e to the natural log of rho is just, it's going to be natural log of rho, or just rho, pardon me, is equal to, and then become e to the minus t over, minus t over tau times some constant. See, because when you take both of these to the exponential power, the e to the c is really a constant, so let's just call it c2 if you want. Can everybody follow me on that? And what you really can say is this. The value of that constant is really going to be just the value of the charge density at 0. Got a comment about this. So e to the minus t over tau times rho v 0. Tau here is epsilon over sigma, and this is referred to as the time constant. You with me? Now, that's very similar to a time constant where you had as 1 over RC. Do you remember 1 over RC for circuits and time decay?
Yes.
Mm-hmm. All right, now, here's where it gets interesting. I like to do this. So, what it's really saying is if you have no sources and epsilon and sigma are constant, If they spatially vary in any significant way, then I can't do this right here. I can't say divergence of J is just this, because a divergence is a differential with respect to spatial coordinates, and if sigma or epsilon varied as well as the D field, then you can't separate it out that way. You have to do more steps. Can everybody follow me on this? Mm-hmm. All right, I want to give you some perspective of the time constant. Let's start with what we're at right now. We're in the atmosphere right here. So for us, in this room, epsilon is about epsilon naught. This is for sea level. I'll just say it's air at sea level. All right. So epsilon is about epsilon naught. Not much difference. But sigma, do you remember me telling you what sigma is down here? Anybody? What's sigma about? At sea level,
I don't recall.
it's about 10 to the minus 14, 10 to the minus 15. It's in that range. You can look this up. It'll get down to 10 to the minus 13 if there's a line of ionization and stuff like this. But you're really talking about, call it of the order of 10 to the minus 14. Bless you. Now, what is the time constant, to give you an idea? Well, tau is equal to epsilon over sigma, right? Epsilon is about what? 8.854 times 10 to the minus 12 over 10 to the minus 14, right? That's 885 seconds. All right. So, if we divide that by 60, we get the number of minutes it takes for one time constant, right? And if we divide that by 3,600, we get the number of hours. It's a very long time. The time constant at sea level, I don't even know what it is, but it's of the, what'd you get?
About 15 minutes.
All right, now, has you ever done this when I was young? We did this all the time at birthday parties. Take a balloon, rub it on your hair, right? And I mean an air film, not helium film. And stick it to the wall, sticks up there, right? What's happening is the charge is inducing charge on the wall, its opposite side, and then it's attracted to that, holding it up. But the charge is decaying at a rate that we can find out. It's a little different than what I'm showing you, but it's close. And you can estimate that that balloon will not stay up there. Basically, you have to write the forces on it. More than about 5 minutes. It'll start to decay down and then just start coming up, drips down. Now, sometimes it's more, sometimes it's less. Has anybody ever done that kind of stuff? You can stick them to the ceiling, stick them to the wall, anything like that. That's what's happening. The charge is leaking off, and that's the equation for it. Probably a good thing to do is at least one or two example problems. Now remember, it can be this form, as simple as this, where there's no sources. They can also do this. They can give you J. Where did I do my divergence of J? I guess I erased it, but if they give you J here, I mean, if you take a divergence, as you get the divergence of J plus d rho dt is equal to 0. If they give you J, you can take the divergence of it, and you got d rho dt, and you can solve for rho. But there are variations in the type of problems that they can ask about this, and that you should at least be able to identify. So, in the back, I think he gives some example. Yeah, he gives you a simple example. Don't worry about that. Let's go to the back of the book, or to the problems in section 5.1. So, let's do 5.3. It's a little different. I'm going to erase this right here. I'll do it in front of you. I heard it's going to rain. I think in my 8 o'clock class around 3 o'clock. There's a 40% chance. Has that changed much?
It's just 30, but it's
30.
still there. Yeah.
Well, what I always do is I look on weather.com, then I look on WeatherBug, then I look on AccuWeather, and then there's Weather Underground. Now, they'll be quite different some days. I mean, to a point where some will say no % chance, the other 70% chance for the same hour of the day. So I don't know the kind of modeling they do. It reminds me of the hurricane models where they'll show you the path of the hurricane after 5 days out. None of them agree. All right, you guys ready for 5-3?
Yeah.
Why don't you guys do it collectively as a class? 5-3. Can you give it to me?
Current density is given by J equals rho e to the minus T over 100.
Okay.
A phi.
A phi.
Yep.
A phi?
No, wrong. A rho. A rho. A rho.
That sounds bad. And that's amps per meter squared.
Yep.
Good.
The initial value of the charge density is 0. Find it at 10 seconds.
Rho v at t equals 0, so if they want to know what rho v is as a function of time, basically, then we'll stick it 10 seconds. Everybody follow the thought on this. So, collectively, how do you go about doing this problem? I'll give you a hint.
Take the
Divergence of J plus the rho v dt is equal to 0. That's a hint. And that's as much as you get.
Okay.
Did you get all your stuff, Zach?
Huh?
Your quizzes and stuff?
Yeah.
All right. If you haven't got anybody, they're outside my office. I mean, there's a wooden box out there, a drop box. Just look in there if you haven't got it.
Yeah, I got all mine.
All right, never mind. That's on me. So how do we do it, guys?
We can take the divergence of J because it's given.
And what is divergence of J in cylindrical coordinates? That's going to be 1 over rho, dd rho, right? Of rho times, really J rho. And then there's other terms. There's partial with respect to
They're
Z.
all 0.
Yeah, that's exactly. You're ahead of me, right? So we don't even write those down because we're lazy. No, because we don't need to. As engineers, we go for the solution that is simplest yet accurate. The more complexity you add, the more likelihood you're going to foul it up. Mathematicians make it very complex, in my opinion, of course. All right, divergence of J is 1 over rho, dd rho, you guys do this, of rho times, what is J rho? Well, it's rho times rho e to the minus t over 100. And so what is that? First, do you all agree with me?
Yes.
Now, I want to say one other thing before I continue. This right here is a trivial problem, but here's where people mess it up, and I promise you they do. They will somehow look at this, and when they do the derivative of this thing, they won't do anything. They'll take the rho squared out in front, and they'll say rho squared over rho, it's rho e to the minus t over 100. They'll do things like this. I don't know why, but people make mistakes. What is the derivative of this going to be? I mean, technically, divergence of J is equal to what? 1 over rho. And what's the derivative of rho squared?
2 rho.
Right, 2 rho, and then it's times e to the minus t over 100 as well, right? Or it's just the divergence itself is going to be 2 e to the minus t over 100. Y'all follow me?
Yep.
All right, now here, so I have the divergence of J here, so I can say d rho v dt is equal to minus divergence of J, or d rho v dt is equal to minus divergence of J, which is going to be minus that minus 2e to the minus t over 100, right? Keep going. What's the next step?
You can move the dt over and integrate both sides, so...
You're exactly right. What we're going to do is multiply by dt and then integrate both sides. Remember, this is an indefinite integral, so we have to add a constant. Okay, and then we'll figure out what it is in a second. So when you integrate this, you get rho v of t is equal to, what happens? Well, I got a minus there, but when I do the integration, I get another minus, right? So I get minus 2 over minus 1 over 100. Y'all agree with that?
Yes.
1 over that a, and then it's going to be times e to the minus t over 100 plus c. Or it's equal to 200, right? 200 e to the minus t over 100 plus c. And now we find out, how do we figure out the constant?
We can use our initial condition.
Which is?
That row of 0 is 0.
Y'all hear? Rho v of t equals 0 is 0. So what does that make the constant? Just by, take a look. Well, it's 0 right at t equals 0. What happens if we get 200? What is e to the 0, guys?
1.
1. 200 plus c is 0, or c is?
Minus 2.
That's right. So you can say just 200 out front, and you can have e to the minus t over 100, and this would be minus 1 would be the form of the function. Didn't he ask for the charge density at what time?
At 10 seconds.
All right, now you'll notice it's going up. Or I should say, at 10 seconds, it's becoming more negative. How's that? It's getting larger magnitude-wise. So what is that going to be? Boy. E to the minus 0.1. So we're going to have 200 times e to the minus 0.1 minus 1. I don't know. I can't. What is it?
Oh, whoops.
Y'all follow me on that?
Yeah, you just plug it in and drug it in your calculator
I
now.
know, but I want the answer.
I got minus 19.
Is it minus 20?
Yeah, I got minus 19, yeah.
Have you
What
posted,
does he have in his book, or his solution?
have you posted the, I don't know if you posted chapter 5
Oh, you got
solutions yet.
Yeah.
You know what? Oh, I don't know.
It's negative 19. In the
All right.
Yeah, that's what I
All right, could you send me an email post chapter 5 solutions? That's on me.
Sure.
I'm sorry.
Do it right now.
You guys good with that?
Coulombs per meter cubed, or what's the units for rho v?
Rho would be coulombs per meter cubed.
Okay, that was right. Okay.
Yeah, it's charge over meter cubed. Now Whitmer likes centimeters, and I don't like centimeters. But, you know, it's his book. So naturally I grumble, but I don't mean to sound critical of him. He wrote the book, I didn't. I've only wrote a few chapters for books in my life. I don't really enjoy all the editing and revisions. But you all with me on this, guys? Okay. Next. Honestly, it's pretty boring, that section from here on. It's just plug and chug, the rest of it. So now we go into Michael Faraday's law of induction. The way Whitmer's book does it, he's going to break it down into two effects. Either he'll cause the B field to be constant and something will be moving, or he'll have the B field time varying and the coil itself won't be moving. So now I'm going to start going through this in a way that makes sense to you. I'm going to try to make this as easy to understand as possible. This is a little more difficult to conceptually get, so please be attentive here. You don't want to mess this up. We'll get to the complete set of Maxwell's equations and the wave equation is set. So, now be attentive here. This is abstract. So we know the curl of E is equal to minus dB dt. Okay? Now I'm going to keep going on this. So try to imagine a surface with a perimeter where I can actually put some conductor around it. This is going to have a surface area of A. And I'm going to assume that a B field is going into the board everywhere here. I have some B field into the board, it's a function of time, but it's not going to be spatially varied. I'm just trying to show you that it's into the board here, and I'm trying not to give you too much information that will distract you from the simple points. Now this is something that is at a point. This is called the differential form of Michael Faraday's law of induction. Now hear me. If I take this and I integrate the curl of E dot ds over the surface surrounded by this wire, and I'll just call this surface S, which is A with an A normal component, that area right there. That will be equal to minus d dt of the integral of the B field dot ds. Everybody with me on that? Kind of abstract. I don't know what you're doing. Tell me why you're doing it. Now, this is called Stokes' theorem. The curl of any function dotted into a differential surface over a surface. If you take the curl of a function dotted into a differential surface vector and integrate it over any surface, it's also the integral of E dot dl over that surface, but it's in the counterclockwise direction. In other words, and I'll spend more time on this, when we do this, we integrate the integral of E dot dl, whatever E is, in the counterclockwise direction. Now please just hear me for a second. I need your attention. Make sure you see what I'm about to do next. Well, the integral of E dot dl around the surface clockwise is going to get a voltage. That is the definition of a voltage, E dot dl. But this would be a gap voltage, and I call it VEMF for now. And that's the voltage. Now notice the sign. If we take and we integrate the integral of E dot dl, it's integral of B dot ds, and it'll develop a voltage plus to minus here that's called VEMF. And I think I should have done something here so I don't confuse you. Can you guys just make a note and have the B field coming out of the board? It'll be easier to understand right now. It's constant, it's coming out of the board. This is going to be the induced voltage developed, but it's a voltage or an electric field, induced electric field that's causing current to rotate this way if allowed. Does that make sense to you?
Wait. So it's coming out of the page?
The B field's out of the page. Now just listen to me. The way I've done this is I'm saying, I don't know what E did.
Yeah.
E could be negative, right?
That makes sense.
But the integral of E dot dl is the integral of this, right here, over the surface. Now to do this surface integral, and I'm trying to be clear about this, when I do B dot ds, what I need to do is this. I have a B field coming out of the board, and I use a right-hand coordinate system. So if you take a look at this, the differential surface here, if this was, call it x, y, z here, x coming out of the board, this differential surface would have components dz, dy, but it would be out of the board in the ax direction. Does that make sense to everybody? All right. Differential surface is always going to have two coordinates that are going to have a spatial component, dx, in this case, dy, dz. That's spatial. The sense of it is the normal component is out of the board, and the way you always get this is just grab this thing with your right hand. Your fingers will curl counterclockwise direction, like you're opening a door knob. The thumb points in the direction of the surface. Do you remember me doing this kind of stuff before? Okay. So if you take a look at this on this side, what I'm really getting is, this is important, VEMF, sensed as I shown, plus on top, voltage minus on. And the reason it is this electric field is trying to force charge around this way. I made a purposeful break here, so now charge accumulates, positive here, negative here, inducing a voltage. And that VEMF will be minus d dt of the magnetic flux. Now the magnetic flux, you can just have that symbol for it. Do you all remember that?
Yep.
So that'll work too. And that's induced EMF for a constant geometry, nothing's moving, and that would be the voltage that would be induced. We'll do some problems like that. Does this make sense?
Yes.
I'm going to show you.
So the induced B field would cause
Not
a current.
induced B field, induced E
I mean,
field.
sorry.
E field.
The B field causes an induced current that goes this way,
And
and the voltage is in the opposite direction
Yeah,
because
but
it's negative.
wait. it's not the B field, it's the time varying effects. This has to be time varying,
Yes,
or else
yes,
there's
yes,
no
yes.
induced voltage.
Yes.
And this is the reason transformers don't work at DC. They have to be time varying field components for a transformer to work. Cannot be otherwise. All right, so this is it. We're going to do a few problems. Y'all with me?
Yes.
But I'm going to say one other thing. Well, we'll do some problems on this one. Then I'll show you when something's moving, what the effect is. So let's see. He has the transformer. So let me get my glasses on. Can you read 5-7 for me in 1 second? I'm going to do it right now. This is problem 5-7 in the book. Give me 1 second.
Alright, in air, a stationary conductive loop is positioned next to an infinite extent line of current as shown in figure 517.
Is that the current I here? You got a loop here, right?
Yeah, it's a square loop with,
Gap.
so it's got, in the x direction, it's A to 2A.
Wait, is this the X direction?
Yeah, it's only XY. Actually, no, that's the Y direction, I'm sorry. It's
XZ?
It's YZ.
Y. This is Y?
Yeah, that's Y, I'm sorry.
And this is Z?
It's on
And
317.
this is A?
Yeah, it's a distance A, and then 2A is the other one.
All right, so this is A and this is 2A out here. Okay, go ahead.
Yeah.
What's the height?
The height is just A.
This is a great one. And this is the voltage right here?
Yeah, and there's voltage, and there's, he's got a resistor, same thing.
He has a resistor.
Yeah, there's a
Yeah,
resistor
it's
on
a-
the loop.
it's a
We'll put
resistor.
the resistor in afterwards.
But
We're going to do is calculate that voltage.
He wants the
Okay.
voltage drop over a resistor, which is,
Same thing as the,
yeah.
go ahead. What's the current?
The line of current increase with time as I of t equals 111 amps per second.
So dIdt is 111. 111?
Is it amps per second t?
111 or 110?
No.
Or 110.
Okay.
I'm sorry.
Amps per meter, right?
Yeah, I can't read it.
That's the IDT, it's all right, I can't read it.
Wait. That says, yeah, that's right.
Okay, then it says if the distance A is 4 centimeters, calculate the voltage R on the loop.
We'll get that in 1 second. First, everybody get this problem in their head. Real important you see this problem. With me? All right, now, for this one, here's how I'm going to do it. First thing I'm going to do is, if I've got a current, I don't care what the value of that current is, it's some I of t, it's going to induce a B field at any given distance rho. It's going to cause a B field, and that B field would be into that page, right? Do you all agree with me there? Right?
So it'd be minus X.
We're going to get there, but just make sure you see what I'm doing. So the B field caused by the assumed current, we're going to have a B field equal to mu, I'm assuming it's there, so it's just mu naught I, it's a function of t, over 2 pi. And instead of rho, maybe I should call it x, because that's what he's using. I'll make it x. It's just the distance from the center there. It's a radial distance, but it can be labeled x. Right? And as was pointed out, it's in the minus ax direction. And that would be Webers per meter squared. Correct, class? Yeah. Now the next thing we have to do, that's going into the board, is calculate the total flux flowing through this loop. Y'all with me?
Yes.
We know we're going to take the time derivative of that. It's got to be done in the right way, so we're going to get our differential surface here. The differential surface would be dy, right? dy, dz, that order doesn't matter. What direction is the differential surface? Positive ax. So it's ax, right? So the B field's in the boards. Now, let me move over here and do the rest.
Is this all just because you assumed a current, you can get all this?
I have to assume a current. I'm going to take a time derivative to get the voltage, but I need to assume a current so I can get the B field.
Okay.
Now, at the end of the day, we're going to take a derivative with respect to time, so only this will be of importance. Bless you. Y'all follow me, class?
Mm-hmm.
All right, so next thing we've got to get is the flux, magnetic flux flowing through there, making sure we're careful to use the right-hand coordinate system. This is a function of time, and it's going to be an integral of B. Now, B is into the board, but it's got mu I over 2 pi x. So it's mu 0 I of t over 2 pi x, and it's minus ax. Then it's dotted in with ds, which is dy dz ax. And what is the limits? Well, dy goes from a to 2a, and dz goes from 0 to a. Do you all agree with me? I'm just putting it in formally.
Wait, dz 0.
Oh, sorry. No, that's right.
No,
That is right.
so it's over 2 pi. Shouldn't that be y? Because this is the y direction.
Yes. So,
Oh, yeah, that's what I was going to say.
that's my bad. Why? I'm so sorry about that. You're absolutely right. The vector is ax, so either minus ax or plus ax. My bad. Thank you very much. You all with me, class?
Yes, gotcha now.
All right. Now, before I do this integral, look, this is the way I do. Set it up carefully. Then do the dot products and just get rid of it. What is ax dot ax?
1.
Right.
Well,
And there's a minus sign. So I'm going to take the minus sign out in front, and I'm just going to erase these, so I don't have to deal with them. Now, after that, I got a minus sign there. The mu 0, can take out in front. The 2 pi I can take out in front. The dz integral from 0 to a just brings out an a out in front. Do you all agree with me there? Then I integrate, then I'm going to get the I of t here. That's a constant, spatially invariant. Then I integrate 1 over y, get natural log, and get natural log of 2a over a, which is 2. So that's my magnetic flux. I usually circle my negative signs so I don't miss them. That's that. Agreed? I don't mean to go so. Y'all agree with me?
Yeah.
Now after that, I'm going to get the induced voltage. Well, VEMF, that would be sensed plus to minus, like I showed you here, will be the time minus the time derivative of that flux. Now you'll notice one thing. Just write it down now. I want you to just, I want everybody's attention when I go through the next step. Everybody with me? All right, look here. When I take the flux here, it's got a negative sign. There's a negative sign here, right? They'll cancel. Do you all see that, class? So I end up with simply mu 0 a over 2 pi. Then I take the natural log of 2 here. Then I take di dt. Di dt, you said is 110, right?
Yep.
All right, so it's times 110. And that's going to be the voltage EMF. What is A again for this one?
It's 4 centimeters.
A is 4 centimeters.
So
All right.
4 to 0, 4 meters.
All right, so for this, mu 0 would be 4 pi times 10 to the minus 7. It's divided by 2 pi. A is, you said, 4 centimeters? Or 2?
4 centimeters.
A is 4 times 10 to the minus 2. And then I got natural log of 2. And then I have times 110. So tell me what that is. That's really 4 pi, 2 pi, give me 2. Times 4 is 8. And then I have minus 7, minus 9. So 8 times 10 to the minus 9 times 110 times natural log of 2. Can somebody give that to me? what I do a lot of times, I use MATLAB for this. I always have mu zero, epsilon zero, all the constants in memory. Right, I'll write it down for Scott.
I got 0.6099 microvolts.
Anybody else? That's about, I think you're right. Oh. Well, let's see, here's how we can do it. Well, it's that, so that's 2, right? Then I have 2 and I have 4, that's 8. So I'm going to have 8. That takes care of those 2. Then I have 10 to the minus 9. That takes care of those 2. Then I have, maybe you're wrong about this, maybe 1, that's 220 times 220. So that's
Wait, no, that'd be 110 times ln2.
Oh, I see. Yeah,
So
you're right.
I got the same thing.
110 times natural log of 2. What did you get?
0.6099 microvolts.
Yeah, and it becomes 8.8 times 10 to the negative 7th times ln2, which becomes.
Anybody see what the answer is?
There's a 0 between the 6 and the 9. No. Put the no. there's-
Point 0.
Point six.
0.60.
Oh,
0.6099.
all right. 0.6099
Yes.
Yeah.
times 10 to the minus 6 volts, right? Yep. All right, what's the book? Anybody?
We don't have it yet.
Don't know.
Neither do I right here. They don't have the answers in the back for that one?
I can check.
Which?
Oh yeah, negative 610 nanovolts, so yeah.
That's it. That's 610, 609 nanovolts. Okay, right answer. Follow me on this, guys?
Yep.
Did you have a question?
No.
Everybody with me?
Is this 5.7?
Yeah.
He's got a negative though. Is there a reason why it would be
Well,
negative?
let me see how he has the voltage. It depends how he draws it. Our voltage right here, just
It
listen.
wouldn't matter if it's positive or negative. That's just how you define it now.
No, well, yeah, but see, this is positive, this is negative. How to show
It's
it?
defined the same way.
Can I see?
This is minus here.
Oh,
He
just
defines
show
it.
me where it is. No. Is that it?
Yeah.
No, he's done it a little differently.
He put it on the other side, I
It
guess.
doesn't matter, but it's going to have a different effect. Watch. So I'll show you what I'm talking about. He has something like this. He's going to have that loop, but he has a resistance here, right?
Yeah.
Isn't this positive
Yeah.
and this negative, right? Off.
Yeah, that would
Correct?
be
Now
negative.
just listen to me, all right? Call this voltage here. That's the voltage difference, right? I just listen to me carefully. Watch this. As I shift it around, see how the positive would be down here? This would be minus if we shifted it here.
Yeah.
All right. What we did is calculate plus minus. That voltage is minus the plus. Do y'all see the reason why?
Yeah, I see why.
You follow me on that?
He just defined it different.
His voltage that he's finding, look, this voltage is doing what? It's driving current in this direction, correct?
Okay. Yeah.
All right, now, for his one, he had a resistance like this, and he wanted plus to minus. Well, guess what? Current's being driven this way. This would be plus, that would be minus. That's the reason. All right? Just look at the direction that this voltage, when you break the circuit, that tells you how charge is going to accumulate. Plus here, minus here. How would the electric field have to be to do that? It has to be trying
It'd
to...
just be, it'd be the same thing. Your B field would be positive AX, right? And you'd have an extra negative that comes back later, or no?
Wait. Say that again? I missed something.
It'd be, since it's backwards, you just have an extra negative that comes back later, or
What were you
like when
saying
the
about what's
current
backwards?
would be in the opposite direction based off.
If the
uniform.
B field flipped, yeah.
Yeah, then the B field would flip.
If the B field instead of going,
Okay.
if the B field instead of going into the board is coming out of the board, the voltage would be opposite. That's
Yeah, more or less.
all right. So that's nothing's moving, but that's just a time varying field, and this is induced EMF. Now the next thing is we're going to get something moving. This is what I just showed you is really transformer action. The next thing you're going to see is something has to do with motional EMF. This is a kind of interesting problem. There's a lot of things happen in the real world where these kind of effects dominate what happens. And this is one of them. This has to do with a lot of stuff. Whenever you get things orbiting, they're moving at a very fast rate in a very low density plasma, but there's a large magnetic field from the Earth there, so they're moving through there fast. So this is the first thing I want to say to everybody before I continue. We talked about if you had a charge, Q, moving at velocity v, and there's a magnetic field B, the differential force was going to be equal to QV cross B. Does everybody remember that?
Yes.
Yeah.
All right, now, if you divide force by charge, differential force by charge, you get V cross B, but what that is, by definition, is the differential electric field. And this is an electric field due to motion. The motion of charge, the B field can be a constant, but the velocity of the charge is really what's allowing this to happen. So what I like to do is say the electric field from motional EMF, that is simply V cross B. That's all it is, and it's in volts per meter. So why is this important? Well, the classic problem is just a bar moving through a magnetic field. Let me see if I can find it. So,
.514,
Yeah.
I think. Conductive bar moving along a pair of.
513 has that diagram.
Yeah.
along in figure 5.7. What is this?
5.7.
513 is more like the bar moving through the magnetic field.
That's right, but I'm trying to, I mean, what, isn't that from figure 518 for problem 513?
Yes.
I got figure 5.7. It's the same thing.
All right, let me look at figure 5.7. What page?
It's on 296. It's got a bar moving away from a
All right, we'll do that one.
voltage.
Let me put it right here. All right. So for this one, this is problem 5. Is it 13 or 14?
14.
5.14.
Or are we doing 13? I don't know.
Which one?
We're doing 14.
Alright, let's do 14.
Doesn't matter. All
It's the
right.
same.
Let's talk about it. So he has something like a resistor here, right?
Yep.
And then he has a pair of rails that go on forever. And he has a bar. And the bar is moving at a velocity v, right?
Yeah.
And it is a B field into the page, right? No.
Yeah, it's that direction.
All right, this has to be given the width. So what is this, or the width, whatever they call it, between the rails?
It just says 0, it goes from 0 to W.
Well, that's W. So
Just
W is the
W.
width.
Just W.
All right, that means it's a space.
Or he doesn't, maybe he might give him the problem. He says it's 20.
21.
20 centimeters.
20 centimeters is the width. Go ahead. What's the B field?
So that was the Y direction.
Good.
The B field is
But
4
down,
AX.
no, but the origin of the Y direction is on the top bar.
Well, it ain't gonna matter.
Yeah. The plus X is downward,
And the Z,
and Z is out of the page.
Yeah, Z's out of the page.
Okay. So that X, Y, Z, yeah, Z would be on the page. All right. So this is a little different. I'm used to seeing, but I don't really care. Tell me about what the B field is. We'll get it in a second.
B field is 4 AX plus 3 AZ Webers per meter squared
4AX plus what?
plus 3 AZ Webers per meter squared.
Here's the reason I'm doing this. I hate the complicated things. So the velocities in the AY direction, right?
Yep.
Yeah.
I want you to listen carefully. All right. When we look at this, the induced, if we take a look at this and we just want to know what the induced electric field is on this thing, we want to know what the differential electric field is induced by that motion. the differential electric field is going to be V cross B. All right? Y'all with me?
Yep.
Now, the length of the bar is in the X or minus X direction, depending on how you want to think about it. You follow me? All right. When we do this, velocity is AY. I'm just going to call it V0 AY. Now, that's the velocity, whatever V0 is. And we got to cross it into the B field. Everybody follow me on this. This part's real important. We did this for a reason. So what's the B field? 4AX, right? Plus 3AZ. Now let's get the differential electric field. Can everybody follow me on this?
So
Yeah.
So it's V naught.
Yes,
Yeah, I got you.
Makes sense. V naught is 3, by the way.
Put it down a second. V naught is 3. I want to just make a point here. This is where the subtleties, I can get my point across with this problem perfectly. It'll eliminate a lot of confusion. When I do this, I'll just leave it as V naught out in front. Now, AY dot AX is,
Minus AZ.
all right, and AY, I'm going to put, it's going to be 4 minus 4AZ. AY dot AZ is
AX.
plus 3AX, right?
Yep.
Now, you take a look at that, that's the differential electric field, right? But, and you could say this, the only component, when we take that which actually, if you want the truth, it's not the differential. It really is the electric field, but it's only acting at a point. This is the electric field that is induced. And I'll just call it motional field, for lack of a better term. That's that electric field that would be at that point. But when we take a look at the actual voltage that would be developed from here to here, just watch this, from point A to point B. So if I want VBA, that's an integral of E dot DL. Do y'all follow me on this? I'm going to show you a couple of tricks.
Would there be a minus sign or would there not be a minus sign?
It's just E dot DL. I didn't define, technically if you want to do it the way the book does it, they always start and they'll put a minus. You can go minus A to B, you're right. But I'll show you how you get the plus and minus in 1 second. If you just pay attention, this clears it up. Are you all with me on this?
Yes.
Now, when you look at this is the axis we're going to integrate on, right? That is the x-axis, right? So when we take this and we dot it into the x component, you'll see how the z component goes away. Do y'all see that?
Yes.
Yeah.
All right. It doesn't matter. So we don't care about the z component. The only thing we care about is the x component. The x has a value of 3AX. So the electric field that we care about has 3AX volts per meter. That would be the electric field that's actually going to cause a voltage. Now look at this. It's pointing in this direction. That's positive X. I want to make sure I got everybody's attention here. Y'all with me?
Yes.
Now look, it's pointing that way, the electric field. The electric field does what? It causes positive charge to move in the direction of the arrow, right?
Yes.
This is positive. This is negative. That's the easiest way to get the polarities. You can't mess that up. Can y'all follow me? He has the electric field, the axis down this way. So that means the voltage will just be the length of that bar times 3AX. It'll be plus on the bottom, minus on the top. So, I'm going to write that. I'm just going to say, if I measure the voltage VB minus VA, which is VBA, would have a plus down there, that's simply going to be that 3 value there times the actual separation distance, which is 20 centimeters or 0.2. It should be 0.6 volts.
Wait.
Spacing is 20 centimeters, right?
Yeah, but wouldn't it be 3 times V naught? So
Yeah.
3 times 3, so it'd be not 1.8, so 3 times that, 1.8.
Sorry, you're absolutely right. I don't mean to make mistakes like that. So that's going to be 1.8 volts. I'm so sorry because of V naught, my bad. But you all follow.
You know what defined?
What's that?
Yeah, it's
Yeah.
3 AY.
He uses a different,
What's that?
he calls it, unusable.
It doesn't matter. It's the velocity. I don't care the symbol he uses. Does he have an answer for that one?
Only the prime number.
So I don't know if he has an answer for the even ones.
That's the thing. I'm sorry, but that's it. Guaranteed. You all see that what I'm trying to do?
So if it says define direction, should we do?
No, you don't need to do that business. The only thing you do is this. Look, V cross B is going to be direction of the electric field, right?
Yeah, and I know the voltage, so the current would be this way. It would be clockwise, right?
Oh, is he asking for current?
Yeah, he asked for
Yeah,
current.
currents. This is the way the currents flow.
And R is 10 ohms. Figure. And so it's
The
just
voltage divided by that limits, the resistance just limits the current. Yeah, you're right about that. Are you guys okay with that?
Yeah.
The big deal is I'm going to give you a bunch of problems and I'll put the solutions up, but you're going to see one thing happens. It becomes obvious. I want to do transformers next. I think I got a few minutes left. And, we're coming down to the last 2 weeks, 2.5 weeks, basically.
2 weeks from today.
yeah.
We're going to get through it. I could see the end, and we're going to get there. I want to just tell you, all right, before I get it, I'm going to do the complete set of Maxwell's equations shortly. But I want to talk about transformers. Now, y'all remember transformers? Did you have them in any of your classes? How many have? Transformers.
Vaguely.
You didn't have? You didn't get them in circuits?
No. Have not taken power either.
All right, don't worry
We got him
about it.
like very vaguely in circuits. He did maybe 1 or 2 days on it.
They talked about it, we didn't do it. It wasn't like, oh, this is going to be on your exam. This is just informative.
No, well, transformers.
Yeah, it's like the day before the
are
final,
important.
Yeah.
Magnetic circuits and transformers are very important. In his book, he's going to talk about transformer action. I'm going to show you how this goes. Now, I'm going to level you. Whitmore's book on this part, he doesn't go very deep. He assumes a whole lot of things are ideal. It's okay, because it's still 99.9% right for what transformers are. A transformer, think of a chunk of iron core. That's what they usually are. They're laminated to stop eddy currents, but don't worry about this. It has a cross section A, and you're going to have a coil of wire like this. This is called the primary. And the current through there is going to be I, and we're going to call it I1, we're going to have N1, the number of turns on the primary. And we're going to have a secondary. And the secondary is going to have N2 turns, and there's going to be, there's a dot here, and I'll get to that in a second. And I'm not even going to connect it to anything, but there's going to be a secondary voltage, and I'll call it V2. The primary voltage is going to be V1. Let me make this a little nicer so you can see it. It's going to have a current I1, there will be N1 turns, and there'll be a voltage plus or minus V1. There'll be V2 on the second. I'm not going to connect it so you'll see what the current is there, but does everybody follow me on this one? Now, if you have a current I1 in the primary, and I'm going to assume that this thing has some total reluctance, just assume the entire reluctance is just R. Doesn't matter what it is. All right? So when you take a look at this, the magnetic flux flowing in the primary is going to be, first I'm going to take N times I, that's the number of turns, times I, and I'm going to take that and divide that by the reluctance. That would be the amount of flux going through one turn. Do you all agree with that?
So if we made a magnetic circuit, would it be like 2 voltage sources, and then, or two like NIs, and then a
If
reluctance
this,
between them?
well, for this one, there is no NI over here if it's an open circuit. I is
Oh, I
zero.
did not catch that it was an open circuit.
Yeah, I didn't want to confuse you right now. So there's only one I, and that's in the primary. With me? When I look at this, NI in the primary over R, that's the flux per turn, and I'll call that I1, N1. Then when I multiply that by N1, that's the number of flux linked on the primary. You all see that?
What are your symbols there? I'm sorry.
N is the number of turns, I is the current, R is the reluctance.
So
And
is that by N1? Multiplied
Yeah,
by
and
N1?
really this is N squared, right? N1 squared I1 over the reluctance is the magnetic flux link in the first circuit. Just call this lambda. You agree with this?
Yes.
Equals still with
All right, now once you have that, we just got into, we said the voltage induced, or V1 in this case, just worry about magnitude now, is really the time derivative of the flux link, right? Remember that? We did the integral B dot ds?
Induced EMF is that?
Yeah, remember we did that? We just,
Yes.
all right. So, and technically it's minus, but I'm trying to just get to the point. So that means when I take a time derivative of this, I have N1 squared divided by the reluctance times, and this is going to be equal to dI1 dt, would be the induced voltage there, right? Y'all agree with that?
Yes.
And we gotta make sure, I gotta see one thing about how we're gonna test this magnetic circuit, just to make sure I don't go too far. All right, in his book, he does put he hooks up a voltage in this, or a resistance in the secondary and has an I2. I'm not even going to bother with it. I'm going to show you something. All right, that's the induced voltage in the primary. Now, here's the next thing. Remember, this is induced voltage in primary. If I take a look at the secondary circuit, and I take a look at the amount of flux coming through here, well, the flux per turn is just NI1 over R. Do you all follow me in this? So for the secondary circuit here, you can say that the total flux linked in the secondary, I'll call that 2, call that primary, and call this or 2 or secondary, that's going to be N2 times the flux per loop, and the flux per loop is going to be equal to N1 I1 divided by the reluctance. Do y'all follow me on how I did that?
Yes.
All right. Therefore, V2 would be the time derivative of that. There's I1 here, so it's going to be N2 N1 over the reluctance times dI1 dt. And now you can see something. Here's V2, here's V1. And if you take a look at these things, you'll notice dI1 dt appears in both of them. You all with me?
Yes.
All right, so I'm going to start here. I'm going to say that V2 is equal to N2 N1 over the reluctance times di dt. Di dt right there is going to be the reluctance over N1 squared times V1. So it's V1 over N1 squared, and it's times the reluctance. Now, by this time, most of you see what I'm up to. You can see what happens is the reluctances go away. All right? And then I get this. Or I get really that has to do with the turns ratio of transformers. This is N1 down here. And you can see that V2 over V1 is equal to N2 over N1. Now this assumes an ideal transformer action, so you can put this down. This is ideal T transformer action. In other words, we're not accounting for losses or anything like that. And there's a lot more to this, but this actually gets you real close. So here's where it comes down. I think I might have time. Does he ask you a problem on transfers? I don't know if he will. Yeah. So if you look at drill 5.5 in the book, can you read that to me? Remember, I'm going to just tell you,
Wait, where is drill 5.5?
95.
It's probably.
it's on page 285. But I want to make it real simple for you. This relates to voltages. All right, so here's the deal. More turns, more voltage, less turns, less voltage. But there's also a relationship between current. I'm going to just put this down. I don't have time to prove it right now. Current is inversely proportional. For current, I1 over I2, since it's inversely proportional, would be N2 over N1. Or you get I1 times yeah, this will be the truth. So it's really I1, N1 I1 is N2 I2, and the product rule. Then you can go and you can get one other thing too, and because voltage, the ratio of voltage to current is impedance, and I'm just going to end with this. I can say V1 over I1. Well, V1 over I1, I can go here, and I can say that, well, I'll tell you what, let me stop here and let me do that exercise before I go down this route too far. Let me do that exercise. I'll talk more about this next time we try to make it clear, and then we'll get into the complete set of Maxwell's equations. But for this drill, was 5.5. What was the answer?
So suppose N1 equals 40 turns. Assuming an ideal transformer, how many turns N2 are required to double the voltage at the secondary?
Anybody. V2 or V1 is equal to N2 over N1. You want V2 over V1 to be 2, right? We got N1 is 40. What is N2? 80. Can y'all see that? That's all it is. And I think that's the right answer. Does he have that? Does he ask anything else?
He asks what happens to the current.
Current goes down. When voltage goes up, current goes down by the same factor. So remember, N1 I1 is N2 I2. Current will go down by a factor of 2. The product of power is the same. Here's the way you think about this. V1 I1 will be equal to V2 I2. You all know the power is voltage times current, right? That'll always work. Now, if you go ahead, you can say that, well, I'll just leave it for that like that right now because I'm about out of time. But I hope you all see what I'm talking about here. It's not really tough. There is one thing I want to say about this. I'm going to give you problems and I'll put up the solutions. Please send me an email. I want to start, want to make sure I cover these problems well. Next time I want to start in the Maxwell's equations and really do a thorough job of doing those. I'll give you problems. We don't have any more days off, right?
Nope.
Good.
So we have this Friday, next Monday, Wednesday, Friday, and then Monday after
2
that.
weeks.
Yeah, we got 5 classes after today.
Yep.
Then we got, I don't even know when our final is.
I have no
It's
idea what it
Friday.
is.
It's the second and the fourth. It's one of those two.
What's that?
It's the second and the fourth. I can't remember.
I think it's
on the
Friday.
syllabus? I didn't see it on the syllabus. Actually,
I don't.
I'm pretty sure both
No.
of your finals are on Friday.
Oh, really?
Yeah, I think so.
Last day finals? Ooh.
Yeah, I know, that's what I said. I was like, wow, I have to stay here till Friday.
We'll have to change that. If I can get away with it. I think I changed that final one time. I have to have unanimous consent. But believe me,